meet with you all today. I'm thrilled that we have this event. Thank you for those involved in organizing. My name's Daniel. I'm a second-year PhD student working with Adam, and today I'm going to be talking about my first dissertation project, which investigates the evolution of iron oxide copper gold deposits using a variety of geochronology techniques, both established and exploratory. So iron oxide copper gold deposits, IOCGs, are broadly characterized by their mineralogy, as they contain iron oxides, copper sulfides, as well as gold, and are formed through hydrothermal processes. In addition to their namesake minerals, IOCGs are of increased importance, as they can also host a variety of resources, other important resources, such as vanadium, cobalt, silver, uranium, and rare earths. IOCGs occur globally and have formed over a wide range of geologic time. And despite their economic importance, there's still much debate as to their origin and formation. So as Jose Tomas and others described earlier, there are two proposed end member models for IOCG formation. There's magmatic hydrothermal, which, as shown on the left, where fluids and metals are derived from a cooling magmatic intrusion, contributions from volcanic host rocks. And on the right, the basinal brine model, where the source fluids are derived from sedimentary basins, heated by an igneous source, and the metals are leached from the sedimentary rocks or volcanic host rocks. And the red arrows on these diagrams indicates the magmatic fluids, and the blue arrows indicates non-magmatic fluids. And there have also been hybrid models proposed. And another important question regarding IOCGs are their relationship with another type of deposits, iron oxide apatite, IOAS, which are often spatially associated with IOCGs. On these figures, the IOA style mineralization are shown in green and consist of magnetites and actinolites and a notable lack of copper sulfides. Association between IOCG and IOA style mineralization is particularly prevalent in the Chilean iron belts, where there's a stretch of IOA and IOCG deposits geographically associated with deeply penetrating fault system. The Candelaria copper mine, which is located in this chain of deposits, is owned by London Mining Corp and is one of the largest IOCG deposits in the world, containing 415 megatons in proved and probable reserves at a grade of about 0.5% for copper and 0.11 grams per ton gold. So at Candelaria, there is a noted change in mineralization style with depth, as we've talked about earlier today. Deeper in the deposits, there's more IOA style mineralization, which then transitions up into IOCG style mineralization, rich in copper sulfides, as you can see in the figure to the right. Recent work by Maria and others from our group measured iron and oxygen isotopes, as well as trace elements in magnetites from Candelaria. And this orange box represents the expected range for magmatic to magmatic hydrothermal magnetites, in other words, high temperature. And so both the magnetite from deep and shallower in the Candelaria plot in this range. So results from this study provide evidence that magnetite crystallized from a cooling magmatic hydrothermal fluid, and a continuum exists between IOA and IOCG deposit types. And as Irene just talked about, there's been her recent work on actinolites from Candelaria utilized the magnesium in actinolite thermometer. And here she discovered at least two distinct pulses of mineralization, with the cores being a hotter temperature and the rims being a cooler temperature. So my study aims to further test this multi-event hypothesis of formation by attempting to directly date minerals. So we utilize thin sections taken from the drill core that I was talking about that extends over 1,000 meters into the Candelaria mine through the IOCG and into the IOA style mineralization. And this cross-section shows the relative location of thin sections from the drill core analyzed in the study. This drill core provides a fantastic window into the deposit at depth and to this transition from IOA to IOCG mineralization. So we all know that the Chilean iron belts, IOAs and IOCGs, are related spatially, but we want to further constrain how they're related temporally. So by directly dating the hydrothermal minerals, we seek to put numbers to the events that others have demonstrated. An even broader question stemming from this is, can magnetites be a useful geochronometer, which Maria shared some of her data earlier. Currently, it's not conventionally used, and there's no externally matched matrix matched standard used during analysis. But since uranium can be incorporated into the magnetite structure, it could have potential. And being able to date the magnetite directly would have obvious implications for understanding the evolution of these deposits, and others too. It could be broadly used in geosciences potentially. So we analyzed apatites, titanites, and magnetites for uranium lead isotopes using laser ablation split stream mass spectrometry remotely at the University of California, Santa Barbara. And for this project, we're concerned with the multi-collector side, which collects the isotopic data. And here's an image of my bedroom laboratory, and many thanks are owed to Dr. Andrew Kylander Clark from the University of California, Santa Barbara, for his ingenuity in remote work during COVID. It was incredible. We were able to access his machine all the way from Ann Arbor. So after processing the data, the first obvious observation was that there's a distinct cluster of apatite and some titanites that are around 115 million years. And this caught our eye quickly because previous work dating molybdenites using rhenium and osmium yielded an age of around 115 million years as well. And these rhenium osmium ages are represented by the yellow bar, and the gray bar in this figure will show the ages of the host rock andesites to give a bit of a constraint on our new dates. This age cluster very likely represents the timing of the IOCG mineralization. Some of the titanites that were dated were distinctly older than the 115 million year events and dated between the ages of sulfide mineralization and the age of the host rock. And additionally, we have an argon dates that we collected at Auburn University in Alabama that yielded a very nice plateau age of 121 million years. These ages, and especially the actinolites, could possibly represent the age of IOA mineralization. And again, not necessarily as one pulse, but possibly several. And so when calculating the magnetite uranium lead ages, most of the magnetites presented geologically reasonable ages, falling between the age of the host rock and the sulfide mineralization. And again, the magnetite dates should be taken with a grain of salt because of the analytical limitations. But I think, like what Maria found, the magnetites in situ laser ablation dates were very exciting because they lined very well with the titanites dates and fell in between the what would be reasonable to expect. So Well, taking a step back to think about the possible origins for the mineralizing fluids, we know from previous iron and oxygen isotopes that the magnetite precipitated from magmatic hydrothermal fluids, or possibly magmatic. Now this diagram overlays our new dates with ages of known igneous activity in the area. Dominantly, it's the Copiapo batholith, which here the different units are represented in the light green horizontal bars, and those were dated with all of those were dated with uranium, lead, zircon. So two apatites overlap with the Los Lirios units of the batholith at around 110, albeit they have higher uncertainties. And the San Gregorio unit lines up right with the 115 million year cluster of ages, as well as the previous rhenium, osmium, molybdenite dates. And the La Brea pulse corresponds almost exactly with the titanite that dated at 118 million years. And the dacitic dikes in the light pink horizontal bar, which predate the batholith, are in line with the actinolite dates and some of the magnetite dates. And then other magnetite states closer to the age of the host rock. So the dates calculated in this study corroborates a multi-events formation model that Irene proposed, and this helps possibly narrow the age of IOCG and IOA style mineralization as seen in the deposit. So future and ongoing work, and if anyone wants to chat about some of this after, we certainly can. So the next steps are to look at the other half of the split stream ICP-MS data, which are the trace elements. And so it's really exciting for each mineral that we have uranium lead isotopes for, we also have corresponding trace elements. And so project going forward will try to determine chemical signatures for the hydrothermal events, much like Jose Tomas and Irene showed earlier. And we'll also try the zirconium in titanite thermometer. Like Maria talked about, there's an increase in vanadium with depth, which is interesting, and we'll just plot some of the discriminant diagrams that have been previously shown today. So lots of exciting work on the chemistry side. And yeah, this has been a fantastic series of